Yesterday I told you about Berger's theorem and his classification of holonomy groups. Today I want to start with a bit more generalities on holonomy groups, and then we're going to move on to Kähler geometry. So the Kähler holonomy groups are U of M and SPM and SU of M. Well, in fact, a Riemannian metric is Kähler if its holonomy group is contained in U of M. And I'm going to spend somehow most of the rest of the course on Kähler geometry because I think it's the part of the subject which is most likely to be useful to you in later life. And then I'm going to spend a few lectures at the end on the exceptional holonomy groups G2 and spin 7, just out of self-indulgence, and I may even miss out SPM, SP1 completely, depending on how much time we've got. Let me first make a few remarks on Simons's proof of Berger's theorem. Okay, so Jim Simons, who hangs out in Stony Brook and is now utterly obscenely rich, before he was utterly obscenely rich, was a quite decent mathematician, and he noticed that Berger's list of holonomy groups looked rather like the list of Lie groups which can act transitively on the sphere. So Simons noticed that Berger's list of holonomy groups is almost the same as the known list of Lie, let's say connected Lie subgroups H contained in SO of N, which act transitively on the n-1 sphere S to the n-1 in R to the n. Okay, so SON acts on here, any subgroup also acts on here. So this kind of means that as far as the group H is concerned, there are no special directions. Any point in S to the n-1 can be taken to any other point under H. So if you're prepared to accept the classification of groups acting transitively on spheres, then that gives you a kind of starting point to more or less recover Berger's list. So Simons basically gave a geometric proof that a holonomy group H satisfying the conditions in Berger's theorem that is, the manifold simply connected, the metric is irreducible and non-symmetric, must act transitively on S to the n-1. So I haven't read that for a long time, so I've forgotten how it works. It is reasonably short, and I didn't write about it in the nearly infallible book, unfortunately. I think you can find an account of it in a rather older book by Simon Salomon on holonomy groups, which goes back to about 1989, I think. It's in the Pittman. Okay, well, so you could try Simon Salomon, a book circa 1980s on holonomy groups, published by Pittman. So I think he has an account of Simon's proof. or you could just read the paper. And so once you've got that, then deducing Berger's theorem is just a matter of eliminating maybe a couple of possibilities which can act transitively on spheres but aren't actually Holonomy groups. So that you might prefer that as a kind of way of understanding where the list comes from. Okay. So next, let's talk about section 2.7 on holonomy groups and Ricci curvature. Okay. Well, we've seen that the holonomy group big H of a metric G places linear restrictions on the Riemann curvature big R of G. So basically, well, the lower A, B, C, D must lie in a vector space curly R big H at each point. So these are kind of candidate curvature tensors. This is the kind of S2 of curly H intersect first Bianchi equals 0, as it were. So it's a vector subspace of S2 of H, where each H lives in the AB and the CD indices, satisfying the first Bianchi. Now, okay, so that we don't know that every element in here can be a curvature tensor of a Riemannian metric, but we don't necessarily care about that. The important point now is that for some, actually most, of our interesting holonomy groups, some holonomy groups H, it turns out that all R, A, B, C, D in this space curly R H are either Einstein or even Ricci flat. So if you look at elements of here, there's a linear map from there into the tensors which look like metrics, S2 of R to the n star, by contracting first and third with the inverse of the metric. And if this is a smallish subspace, then that map may be 0. So, well, it turns out that, well, firstly, metrics with holonomy contained in SUM are Ricci flat. So, well, I'll be explaining this in rather more detail later when we get into the Kähler holonomy groups. Yeah, and well, as an aside, when you're talking about things with holonomy, most statements you make are true not just for a metric with a given holonomy group, but also for a metric with whose holonomy group is a subgroup of that group. So you get used to writing holonomy contained in something if you want to make more general statements. So a metric with holonomy, well, let's say G, whole G contained in U of M, so that G is Kähler with respect to some complex structure, is Ricci flat if and only if well, in fact, the reduced holonomy of G is contained in SU of M, which then implies the holonomy group of G is contained in SU of M if X, your manifold, is simply connected. Okay, so the Ricci curvature of Kähler-metrics is really the difference between something which is holonomy group in U of M or something which is holonomy group in SU of M, which is broadly Calabi-Yau, depending on your exact definition of Calabi-Yau. Okay. Secondly, metrics with holonomy contained in the quaternionic unitary group SP of M are also Ricci flat. So actually this follows from A. As SPM is contained in SU of 2M with equality if M equals 1. Okay. Thirdly, metrics with holonomy, now I'm going to say equal to, not just contained in, SPM, SP1. These are Einstein. But actually not Ricci flat. So if you had a metric with holonomy contained in SPM SP1 and it was Ricci flat, then actually the holonomy would reduce to SPM, at least up to the fundamental group, so the reduced holonomy would be contained in SPM. So somehow the SP1 factor here necessarily contributes a non-zero Einstein constant if it's present. Okay, and then finally D and E, let's say, metrics with holonomy G2 in 7 dimensions and spin 7 in 8 dimensions are also Ricci flat. Okay, so that's kind of nice. I mean, there's various reasons to feel that Einstein metrics or Ricci flat metrics are kind of, in some sense, the best kind of metrics you can find on a given manifold. You know, they're stationary for the volume form. Oh, sorry, they're stationary for the volume. Do I mean that? Stationary for something or other. Yeah, they're generally kind of nice classes of metrics, and then you automatically get these out. Okay. Next, let's say something about holonomy groups and G structures. So let me remind you of a few things I told you earlier in the week. So let's say X is an n-dimensional manifold. F can be the frame bundle of X, which is a principal GL n, R bundle. And let's say G in GL n, R can be a Lie subgroup. Then a G structure on X is some P contained in F, which is a principal subbundle with fibre G. That is, P is an embedded submanifold of F. It's fixed under the G action on F induced by the GLNR action, and then the G action on P and it's mapped down to X make it into a principal G bundle. That's what I mean by a G structure. Also, well, a connection H on F, the principal, the frame bundle, is some vector subbundle H sitting inside T, the tangent bundle of F, satisfying some conditions. So the conditions being that H is invariant under the GLNR action, and the tangent bundle of F is a direct sum of the vertical subbundle and the horizontal subbundle H, where the vertical subbundle is the kernel of the map from TF into the pullback of TX. That actually implies that H is now isomorphic to the pullback of TX. Okay, well, so that's much I've said already. Well, so we say that P is compatible with H if H restricted to P, this is now a vector subbundle of the tangent bundle of F restricted to P. This is contained in the tangent bundle of P, which is contained in the tangent spaces. So at each point I want the fibre of H, which is a vector subspace of the tangent space to F, to be a subspace of the tangent space to P at that point. So then, sorry, that's not a P. Oh yeah, that's okay. Then H restricted to P is a connection on P. So certain connections on the frame bundle can be restricted to connections on the principal bundle, the G structure bundle. Now also, there is a one-to-one correspondence between, well, so principal bundle connections H on the frame bundle F and vector bundle connections nabla on TX, which, and you can recover TX from the frame bundle F as the associated vector bundle of the usual representation of GLNR on R to the n. So okay, so I didn't really explain this particularly, but this is true. And nabla has a torsion tensor T ABC. So therefore any connection H on F also has a torsion tensor T ABC. So you can ask, so does well, let's say if P is a G structure on X, so does there exist a torsion-free connection, well, H, which is equivalent to some nabla on F compatible with P. And if it's yes, then we call P torsion free. Okay, so this gives us a notion of torsion-free G structure. Okay, so now in general, well, for any G structure, P, there exists connections H on F compatible with P, and then H gives you some torsion T, A, B, C, and you can split T as into two components, T1 direct sum T2, lying in different vector subbundles of the vector bundle of possible torsion tensors, such that basically T1 is the same for any H compatible with P and T2 varies with H and we can in fact choose H such that T2 equals 0. Okay, so there's the torsion falls into two bits, one of which depends upon P, the other of which doesn't, and there's enough freedom to actually make the second component 0. And then we define what we call T1 the torsion of the G structure P, and in fact, so this is, and then T1 equals 0 if and only if P is torsion free, in the obvious way. Okay, so we're living in this world of principal bundles and G structures, which is perhaps slightly more abstract than vector bundles and metrics, but it's quite a powerful point of view in some ways. Okay, so let's look at how this relates to holonomy groups. Okay, so let X and G be some Riemannian manifold with holonomy group of G is some big H, or actually contained in H will do, contained in SON. So then, well, so implicitly, the kind of the inclusion hol of G contained in SON means we've kind of chosen an identification Tx0 of x is isomorphic to R to the n, at least up to the action of H. So we've got some special class of identifications between that and this. Okay, it's possible I'm lying a little bit here, but I don't care. That's what I want, anyway, to make that choice. So now, you can now define an H structure, P on X, as follows. Some a point little x, E1 up to En lies in P. Oh, so this is in the frame bundle F. This lies in P if, well, whenever gamma going from 0 up to 1 into X is a piecewise smooth path from the base point x0 to the point x we're interested in, then, well, P gamma inverse of the basis E1 up to En is equivalent up to the action of H in SON with the standard basis of T x0 of x, which we're identifying with R to the n. Okay, so this R to the n has got its standard basis of 1, 0, 0, 0, 1, 0, and so on. We translate that to a basis of Tx0 of x. So that gives us one possible basis of that. We're allowed to act on that with an element of h. That gives us a family of bases here. We want these guys we want to look at points in the frame bundle which are translated to things of that form.
So it's just from x0
to x. Well, so x is just some point in the manifold. x0 is the base point which I chose to define the holonomy group with. So, okay, so and the reason this definition is independent of the path is that if I chose two different paths from x0 to x, then going round them, one in the opposite direction, will give you a loop based at x0, and the parallel transport around that would lie in h, because the holonomy group is contained in h. And because I'm allowing myself the freedom of moving my bases around by h, that means that two different paths from x0 to x are going to give parallel transported bases differing by the action of h. Okay, so this is at least well defined. Okay, so then it's a fact that this P is a torsion-free H structure on X, and there's a unique torsion-free connection. Well, sorry, I've now got two H's. Well, so H here is being a Lie group. Sorry, yep.
What if we don't take what if we just do the thing we did at x0 at x1? So asked for bases at x1 that equivalent the action the standard basis of Rn. Why do we need to go to another point in parallel transport?
Well, because I'm defining my holonomy group as a subgroup of Tx0 of x.
Okay.
Which I'm identifying with R to the n. I don't have a given identification of Tx1 at x with R to the n. Okay. So I'm using this parallel transport to tell me how to identify different tangent spaces with the standard vector space R to the n. Okay, so there's a unique torsion. Sorry, I've been using H for my principal bundle connections because it means horizontal subbundle. I've also been using H for my holonomy groups as it means Lie group. So on these boards, H is something different. Maybe we should just change these H's to G. G is a Lie group. Sorry? Well, you can take the Holonomy group to be equal to G if you like, but it's also true only if the Holonomy group is a subgroup of G. So G is going to be any Lie subgroup of SO of n, and the Holonomy group has to be contained in it. Okay. Okay. Sorry.
Is the H up there? I'm back on that.
Oh, okay. I really don't care. Okay, so H can mean either a Lie group or a connection. Anyway, so P is a torsion-free G structure on X. So there's a unique torsion-free connection nabla on, well, F compatible with P, which is just a Levi-Civita connection of the Riemannian metric G. Okay, so there's this kind of rather abstract point of view which says that holonomy reductions gives us torsion-free G structures, and you know, this is maybe all I'll say about this for now, but it's something which can come back later. If you're trying to construct, for example, metrics with holonomy G2 or spin 7, what you'd actually do is you'd build G2 structures or spin 7 structures on your 7 or 8 manifold, which are not torsion-free, but you then have this geometric quantity, the torsion T, which could be basically the derivative of some things which you actually want to be constant but which weren't, and then so the torsion is kind of the error, and then you try and deform them from you'd measure the torsion in a Banach space, you'd construct G2 structures, let's say with small torsion, then you want to deform them, the G2 structures, with zero torsion. So this point of view of G structures with torsion is a very useful thing for actually constructing G structures by gluing, deformation, that sort of thing. Okay. Right, so shall we move on to start talking about Kähler geometry? Yeah. So we're going to spend several lectures talking about Kähler geometry and the Kähler holonomy groups. So Kähler metrics are a kind of Riemannian metric on complex manifolds. But they have holonomy contained in U of M, where U of M is obviously the group preserving both a Riemannian metric and a complex structure on R to the n, R to the 2n, or 2m. So section 3 on complex and Kähler geometry. So I'm going to spend quite a long time just explaining about complex geometry and Kähler geometry, because I think it's a good thing for you to know. So we'll start off by talking about complex manifolds. So manifolds of complex structures, and then later on we'll put the metrics on them as well, and those will be Kähler. So, Kähler metrics are the most natural class of Riemannian metrics on complex manifolds. So we'll start with two different but ultimately equivalent definitions of complex manifolds. So the first definition would be somehow the natural definition from the point of view of complex analysis. If you started off thinking about holomorphic functions on C and C to the n and so on, then this is how you build your definition of complex manifold. And actually, well, if you take the definition of manifold, you get a topological space, satisfying some global conditions, and an atlas of charts. And the charts consist in open subsets of R to the n, and the transition mapping into your topological space, and the transition functions have to be smooth. But that's quite a versatile definition. You can replace subsets of R to the n and smooth maps between them with all kinds of other things. You could use subsets of R to the n and C to the k maps between them, get a notion of C to the k manifold. Or you could take subsets of C to the n and holomorphic maps between them. That will give you complex manifolds. Or you could take open subsets of some Banach space and then kind of Banach smooth maps between them and define Banach manifolds and so on. So the definition of manifold, you can kind of insert your favorite notion of manifold, or even manifold with corners, and so on, into it, and whenever you've got a kind of category of things like things looking a bit like R to the n, you can get a thing like manifolds. So here's our first definition. So a complex manifold is a Hausdorff and second countable topological space big X with a holomorphic atlas curly A. As for real manifolds in the first lectures, I'm going to write this as a set of pairs ui phi I, where little I lies in some indexing set big I. So now ui, instead of being in R to the n, is going to be in C to the m as an open set, where m is the complex dimension of X, is some fixed natural number. And, well, again, phi I, going from our set ui into X, is a continuous map of topological spaces. It's a homeomorphism, an isomorphism in topological spaces with an open set the image of phi I contained in X, and the transition maps so phi j inverse of phi I, which now map from some open subset of C to the m into a different open subset of C to the m, basically the largest subsets on which the transition map can be defined. These have to be holomorphic. For all I and j in the indexing set big I. So that's just the same as the definition of smooth manifold, but we have ui's and C to the m instead of R to the n, and we have holomorphic maps instead of smooth maps. Okay, so that's kind of complex analyst's definition of a complex manifold. But what I'm perhaps more interested in, from our point of view, is a kind of real differential geometer's definition of a smooth manifold, which is of a real smooth manifold together with an additional geometric structure. So let's make a second definition which is that of almost complex structures. So complex structures and almost complex structures. So we'll define almost complex structures first. A complex structure is a special kind of almost complex structure. So let big X now be a real smooth manifold with the real dimension of X is going to be even. So let's take it to be 2 times m. So m will be the complex dimension of X. So then an almost complex structure is a tensor J. In index notation, it's J, let's say lower a, upper b, in the smooth sections of the tangent bundle tensored with the cotangent bundle. We think about this as an endomorphism of the tangent bundle, so it's something which maps from the tangent bundle into the tangent bundle. And as an endomorphism, it has J squared is minus 1 or minus the identity. Or in index notation, we have J a lower a upper b, J lower b upper c is minus delta a c. Okay, so that's an almost complex structure, and the almost complex structure makes each tangent space of X into a complex vector space in which J gives you multiplication by little I, the square root of minus 1. So it turns at least the tangent bundle of X into a complex thing rather than a real thing. And we call the pair X, J an almost complex manifold. Okay, so next let's define, we say that some smooth function, that little f, going from x, f, which can also be u plus I times v, f going from x into the complex numbers, so u is the real part, v is the imaginary part, is holomorphic if on the derivatives j lower ab times dv b is equal to dua. So this is just the kind of standard Cauchy-Riemann equations of complex analysis, at least if you do this, let's say on if x is a complex numbers was the obvious almost complex structure. Okay, so there's something called the Neuenhaus tensor. At least you guys probably know how to pronounce Neuenhaus better than I do, because I think he's Nordic. The Neuenhaus tensor Nj is the obstruction to the existence of many holomorphic functions locally, meaning in small open sets. So it can happen that you get an almost complex structure which is kind of bad, and then there are the only holomorphic functions in any open set are just constant. Okay, and that's when the Neuenhaus tensor is kind of maximally non-zero, as it were. Okay, so it lies in the sections of Tx tensored with lambda 2 t star of x. So it's tensor of the type NABC, with NABC is minus NACB. Is that right? Yeah. So it looks rather like a torsion tensor, and in fact it is a torsion tensor. So perhaps I'll give you, so in fact, almost complex structures are equivalent to GL M, C structures in the sense of G structures I was telling you about, and then N is actually the torsion of the G structure, of the GL MC structure. Okay, well, so we've got to 10:30, and I will give you a proper definition of the Neuenhaus tensor, but perhaps I'll do it after the break.